Hi, I'm Dick Collins. This program is on the Garmin G1000 glass cockpit that's installed in virtually all new Cessna Skylines built for domestic use. The 206 and the Skyhawk followed the Skyline in sporting the G1000. What we're going to do here is give you an overview of the system. There is so much capability in the G1000 that the ground school on it runs at least 4 hours and the manual is a big, thick book. The G1000 has two screens. On the left, in front of the pilot, is the primary flight display, the PFD. The multifunction display, the MFD, is on the right, though if there were a problem with the primary flight display screen, this presentation can be moved to the right screen with the press of a button. The G1000 is basically operated with knobs, joysticks, mechanical keys, and what are called soft keys because they're defined by software. With soft keys, the label for the mechanical key is shown on the screen and changes depending what function you have selected. The keys are all menu-driven. Items are listed across the bottom with the defaults as shown. For example, if you want to change things on the PFD, you press that soft key. The menu then gives some of the choices of things to change. Select whatever you want using the cursor and the large and small flight management system, FMS, concentric control knobs at the bottom right of the PFD. Pressing on the end of the FMS knobs activates the cursor. Basically, the large knob moves you between areas of selection and the small knob operates within those areas. When you get the cursor on what you want, press the dedicated Enter button and presto, that change is made. These controls have been on navigators for a while, and for years the manufacturers confused them by calling them the outer knob and the inner knob. Garmin got it right, calling them the big knob and the little knob because, well, one knob's bigger than the other one. There's also a menu button that, when pressed, will give you a menu for things that you can do in relation to the screen that's on display. For example, when looking at a flight plan on the MFD, the menu will give you the option of activating or inverting the flight plan and activating it, among other things. Once you use the system a few times, these things will have some logic to them. We go flying a bit and show you how some are used. Many of the things you change to configure the G1000 to your personal preferences will not have to be changed again. If you are coming to a Garmin from some other brand, there's one thing to stumble over. On this Garmin, some actions take 2 presses of the Enter button to be fully entered. The Direct To function is one of these. You have to enter the waypoint, press Enter, and then press Enter again. Let's now look at the big picture on the PFD. Here we have the same information that we've been using to fly since we started flying IFR and piston airplanes. With the G1000, though, it is prepared and presented differently. Before, for the most part, we used gyros driven by a vacuum pump as well as a pitot-static system. The G1000 gets attitude and heading information from an AHRS unit, that's standing for Attitude and Heading Reference System. Instead of gyros, it uses advanced sensors, accelerometers, and rate sensors to develop the same information, only more accurately and more reliably. Then there's an air data computer. This gets information from the pitot-static system and outside air temperature sensor. It computes pressure, altitude, airspeed, vertical speed, and outside air temperature and feeds this information to the G1000 for computation and display in the appropriate places. So we're getting our information in a different but much more precise and reliable manner. There's more information too. It's been done this way on turbine airplanes for years, but now it's coming to a piston panel near you. Navcom information is shown across the top of the PFD. The frequencies are selected much like with any Navcom, with an inactive and active frequency display and a control to flip-flop between the two. There are 2 each navs and comms, and either can be tuned from the PFD or MFD. The tuning control is pressed to toggle between 1 and 2. Drop toward the bottom of the screen and you see a familiar horizontal situation indicator. This can be displayed either in the 360-degree mode or the arc mode. That's one of those choices you will probably make only once, to whichever format you like best. The arc mode in this application looks hokey to me. Now, moving up, we find attitude in the center with airspeed to the left and altitude and vertical speed to the right. The attitude display is not a picture of our artificial horizons of old. Here we have a yellow triangle representing the airplane with the blue sky and brown earth depiction running all the way across the screen. The tip or top of the triangle is the nose of the airplane in a level attitude. You'll notice that the pitch scale is large, which makes accurate pitch control easier. If ever you really goof and get in a nose up or down attitude where the delineation between blue and brown would be gone or almost gone, 50 degrees nose up or 30 degrees nose down, red warning chevrons appear and point toward the horizon. The supplementary boxes, the inset and the alert box, drop off the screen when this happens. It is almost impossible to lose pitch control without first losing bank control, so if these chevrons show up, there'll be a lot more to do than just adjusting the pitch attitude. The yellow wingtip displays on either side of the inverted V won't help you in pitch control when the airplane's banked, but they do help in roll orientation. This attitude display gives a far bigger picture, and use of it should be intuitive. A word about the attitude indicator. The airplane symbol is like that used on a single Q flight director, but there is no flight director in this installation. Stay tuned, though, because everything changes with time. At this point, many pilots raise a question about the turn coordinator. It does not appear to be there, but it is, though not at all like we see it on an old airplane. The skid information is that white line beneath the roll pointer. It displays slip and skid. If it is skewed to the right, that means the same thing as if the ball is displaced to the right. The turn rate indication is at the top of the HSI compass card and shows half and whole standard rate turns. This would seldom be used because a rate of turn indicator is used mainly when there's a problem with attitude indication, and with a system like this, the most common failure scenario would be all or nothing. Just like you don't look at a turn coordinator when flying visually, you won't when flying with the G1000 because its attitude presentation makes flying more, well, visual. I shouldn't have said there's no turn coordinator because that is not precisely correct. There is one, but it's behind the panel and is used only in the operation of the rate-based Bendix King KAP-140 autopilot in this airplane. Next, we come to what people think is the hard part of flying with a display like this, but it's really just different, not hard. On the left, we have the vertical tape depiction of airspeed with the low numbers at the bottom. The depiction is coded just like a mechanical airspeed with white, green, yellow, and red. Bugs are also provided to identify key airspeeds. The default settings are for VR, rotation speed, VX, best angle of climb speed, VY, best rate of climb speed, and the best glide speed. These can be changed if desired, though it's hard to see a reason for change. On larger airplanes, they are adjusted on each takeoff for weight and density altitude, but light airplanes are not often flown with such precision. Any individual bug can be turned on or off. When the airspeed is changing, a magenta trend line is displayed that shows where the airspeed will be in 6 seconds if the current rate of change in airspeed continues. There's a lot of information here, and at first pilots might sneak a peek at the old-fashioned airspeed indicator in the low central portion of the panel. But controlling airspeed using the vertical tape format is not difficult, and G1000 pilots will get used to it in a hurry. At the bottom of the airspeed display is the true airspeed readout. That's a neat thing to have, and the readout is just one more reason we don't use handheld computers as much as we used to. We've got a vertical tape display of altitude on the right side, and it's the same deal. The lower altitudes are at the bottom. There's a baro setting box at the bottom, and there's a baro knob to the right of the screen to set this. There's an altitude reference box at the top. This is set to the altitude to which you're climbing or descending or which you're flying level. A bug on the altitude display reflects this altitude. This selected altitude has no influence on the KAP-140 autopilot, which must be set separately. Altitude selection for the G1000 is done with a knob at the lower left of the PFD. Altitude selection for the autopilot is done there. There's an altitude trend vector that works like the one on the airspeed in showing where the altitude will be in 6 seconds with the current rate of change. The vertical speed is to the right of the altitude tape and has a pointer as well as a numeric readout. Glide slope indication is shown just to the left of the altitude tape. A couple of other standard things. There's a little strip box at the bottom right that shows the selected transponder code and indication of function, that altitude reported is selected, and the indication that the transponder is being interrogated. Next to that is a system time box. The satellites provide the time, and all the pilot can do is select local 12-hour, local 24-hour, or Zulu time. There is only one transponder fitted, which, in this day of regulated airspace, seems like false economy. For many flights, an inoperative transponder is a no-go item. Additional items can or will be shown on the PFD. One is an inset map at the lower left, which is a smaller replication of the big map on the MFD. The range shown on the inset is controlled from the PFD, and because of the small size of the picture, it would probably most often be used for close work, as, for instance, orientation during an instrument approach. Turn it on or off with the inset soft key at the bottom left of the PFD. Icons in the lower right corner of the inset tell you that the traffic, terrain, and lightning functions are being displayed. Over on the other side of the display, there's an annunciation window where annunciator items such as low fuel or vacuum or volts are spelled out. Below that is an alerts window. Word that there is something there comes from flashing of the alert soft key annunciation. The importance of the item is identified, warning, caution, or advisory, and the pilot can view the message in the alerts window. This is something really new for piston airplanes. On the way over to the MFD, let's pause for a moment at the standby instrument panel. These are familiar instruments. The artificial horizon is vacuum-powered. The airspeed and altitude run off the pitot-static system. This is what you would use if all the lights went out, which should be highly unlikely. We'll look at the electrical backup for the G1000 in a bit. The audio panel is in the center, and we're not going to spend time on that other than to say that with some versions of the system, the pilot and co-pilot can use comms for different purposes at the same time. This feature was not approved on the Skyline when this program was prepared, presumably because the communications antennas are too close together. Also, there's a red button at the bottom of the audio panel that's used to move the PFD display to the MFD screen. If this is done, the display includes the engine instrument stack that is normally on the MFD and which we'll talk more about in a minute. At the MFD, we find a whole bunch of new things, but for pilots who've been flying with a Garmin 430 or 530, a whole lot of familiar things. The MFD has all the same controls as the PFD, so there's nothing new to learn there. However, because it has an entirely different function, the soft keys are different. The MFD has all the engine and systems information as well as navigational and other information. The scoop on the engine is in a stack at the left side of the MFD. Here it shows everything you need to know about what's going on. All the things we have had in the panel are there, plus word on the amount of fuel used since engine start, a continuous readout of the bus voltage, and when the standby battery is in use, the voltage there, plus an ammeter for that system. In the event one screen were to fail, the inclusion of the engine indication stack on the left side of the PFD would meet all the requirements for continued flight. When the lean soft key is pressed, the system brings up the EGT and cylinder head temperature indications, including word on the EGT of the leanest cylinder in relation to peak. This is what you would use to lean the mixture. Precise leaning is pretty easy with this system. Cylinder head temperature is included on the primary engine display, but only the hottest cylinders shown and identified. This is also true of the EGT indication. To look at all 6 cylinders, you need to consult the lean page. The system will warn of low fuel in either of the 2 wing tanks. An amber warning comes when the level in the tank gets to 8 gallons. It turns flashing red when the tank is effectively empty. The pilot's face should do the same. There's a fuel totalizer system, but it will only count down from full tanks. The system will look at all factors and put a fuel range ring on the map. A dashed green ring will show the range with 45 minutes reserve fuel. That's the default setting. The reserve ring can be increased by the pilot if desired. A solid green circle indicates the range of all fuel, including reserve fuel. This feature would need to be used carefully because if the fill-up didn't get the tanks quite full, it could be misleading. The larger part of the MFD screen is devoted to a map on which traffic, topography, terrain, and lightning can be displayed along with any flight plan or procedures such as departure, arrivals, or approaches. Topography means that it's showing selected features on the ground, including roads and towns and railroad tracks. Terrain means it's showing the height of the terrain in relation to the height of the airplane. Red is a bad color. More on that in a minute. The MFD displays information in 4 main page groups: map, waypoint, auxiliary, and nearest. There are choices within each page group. Under map, for example, there's the navigation map page, plus a traffic, a weather, and a terrain proximity page. Traffic and weather can and should be simultaneously displayed on the navigation page, but, for example, were you flying in an area with a lot of traffic, you might want to select the traffic page and just show that. For now, the weather page shows only the output from StormScope, but work is underway to add XM weather, and as soon as that is ready and approved, it will be installed at no additional charge, and we'll add coverage to this program. For now, we have an Airfax program on the uplink downlink of weather. When you're in any of these pages, a press of the menu button will display options or tell you if there are no options. If you want to make changes, use the cursor and the FMS knobs. The page for waypoints offers information on everything, including airports. Frequencies can be transferred from any informational page to the nav or comm radios through the use of the FMS knobs and the cursor. The auxiliary page features things like GPS status and altitude, RAIM availability, which is word on whether or not the signals are good enough to use for an approach, trip planning, setup, status, and utility items. Then there's the nearest page group, which is exactly what it sounds like. The nearest airports, nav aids, frequencies, and regulated airspace can be shown here. There's a procedures button that brings up screens through which you select departure, arrival, and approach procedures that you want to use. Again, everything is menu-driven. Whatever screen you're looking at, a press of the menu button will offer word about what you can do to or with that screen. There is, for example, a page where you can select what you want shown on the map at the various ranges. Most owners will customize the map to their liking and never change it again. If it's a club or rental airplane, the best deal would probably be to agree on what will be shown and then leave it alone. Having gone through all that, let's go flying and see how it works. Getting the airplane in the G1000 up and running involves some new checklist procedures. These are mainly related to the fact that the system has a standby battery and has, for avionics, 2 main buses and 1 essential bus. On some airplanes, the latter is called an emergency bus, and that's what it really is, but the PR department obviously named it on this airplane. Before starting, and with everything else in the airplane turned off, the standby battery switch is held in the test position for 20 seconds, and it's verified that the test lamp does not go out. This switch is spring-loaded when in the test position, and that's 1 strong spring. After 20 seconds, the standby battery switch is put into the arm position. The PFD, which along with the air data computer, NavCom 1, and engine instrumentation, is operated by the essential bus. It comes on. When the PFD is there by itself, without the MFD, the engine indicating system is included on the PFD, and in pre-flight it's verified that there are no red X's through the engine page indicators. Then, essential bus voltage is checked as on 24 minimum with the main bus voltage at 0. The standby battery amps are checked as negative with the standby battery annunciator on. Then the master switch is turned on and the engine started. The main and standby batteries are checked for a positive charge, and the avionics switches for bus 1 and bus 2 are turned on. When this is done, the PFD switches to power from the primary system. If anything is not working properly, the warnings are plain to see. Were the voltage in that primary electrical system to drop below a usable value because of a charging system failure followed by a discharged battery, the standby battery would automatically come on and power the essential items only. Question: after a charging system failure, how long would the main battery and then the standby battery last? The FAA requirement is for 30 minutes total, and Cessna says, but not in the POH, that is how long the standby battery will last on the essential bus. The standby battery is continuously charged, is located behind the instrument panel, and is essentially comprised of rechargeable flashlight batteries. Where unessential items shut down, there's no question that the primary system would operate for longer than 30 minutes on the main battery before the standby would kick in, so that gives useful time. After a charging system failure, the drill would be to shed as much load as possible to preserve that main battery for as long as possible. One avionics bus switch could be turned off with the affected items clearly visible on the circuit breaker panel. The most likely choice would be bus number 2. Regardless of which bus is turned off, there would be a PFD in view with the engine indications on display. There's little other load to shed, only lights and pitot heat controlled by individual switches. With the charging system inoperative and with everything getting power from the main battery, when the voltage drops below a set value, the system automatically switches to the standby battery and the essential bus. Automatic load shedding, in other words. It should be noted here that there would be no transponder and no lights when operating on the essential bus, so a pilot would be best advised to tell ATC what might happen before it happens. Also, the transmitter power is reduced to 10 watts to help preserve battery power. It would still be advisable to transmit as little as possible. The transponder isn't included on the essential bus because of relatively high current draw. The PFD would be all lit up, so 6 flashlights wouldn't be necessary except to see other things in the cockpit at night. There would be no cooling fan operating on the PFD either, which probably wouldn't make that much difference in the relatively short period of time that the system would run on the standby battery. They can call that bus essential if they want to, but emergency is a better word. And without question, were the charging system to fail, the only thing to do would be to land at the nearest suitable airport and get it fixed, which is the advice given in the POH. The goal should be to get on the ground before the system automatically reverts to the essential bus. Failing everything else, there's always the standby instrumentation and the handheld transceiver and GPS that no IFR pilot should fly without. I'll add one thing. If one of these airplanes were in my hangar, I'd power up only the essential items and see how long the main battery would last without the charging system running. That would only cost the price for battery charge, and I'd at least have some idea of how long the main battery would operate after a charging system failure. We do need a good understanding of the electrical system because with a glass cockpit, we're more dependent on that system. The voltage in a system like this runs at 28 and change when the charging system is operating. The warning of low voltage is given somewhere between 24.5 and 28 volts. The battery puts out 24 volts maximum, so at any time the system is operating on the battery alone, the warning of low voltage will be given, even though the voltage might not yet be really low. That does not in itself indicate that the end is near. It's just getting ever closer. The G1000 components will operate at a much lower voltage than 24. Most have a low voltage limit of 11 volts, and by the time the voltage is down to 9, everything would be gone. The digital voltage readout thus becomes important. It is telling you the status of the batteries. Lead-acid batteries do not run down in a precise linear fashion, but with the voltage readout you can get an idea of how things are going. To begin, before flying, let's configure the system to be all that it can be, or at least all that we want it to be. We want to make sure the inset shows on the PFD that the traffic and lightning detection systems are turned on and that the topography will be shown with all desired features activated. One word on traffic. This is a traffic information system that uses an uplink from terminal radar control facilities and the onboard Mode S transponder. That means that you have to be in range of a TRACON to get traffic information. When information is unavailable, that is enunciated. One other thing I want to address here is the auto zoom feature. This automatically reduces the range of the map as you draw closer to a waypoint. It frankly drives me nuts, and I can't disable this function soon enough. I would rather control range myself, and while I do reduce the range as I get closer, I like to be in control of that. Other pilots love auto zoom. You'll have to decide for yourself. As you've been able to see, it is simple enough to disable. You can also see that there are a lot of other map choices on this page. I'm a track up man, so that is selected and everything else is left turned on. For this first takeoff, the pilot flying is in the right seat, so the reversionary mode is selected using that red button at the bottom of the audio panel, so that the pilot flying has the PFD and the engine gauge stack in front of him. With 2 pilots on board, I would make every takeoff like this so both pilots would have a full set of flight instruments to use. Using flight plans is an integral part of any navigational system, and a pilot who doesn't use flight plans simply doesn't get his money's worth out of the equipment. The G1000 will store 99 flight plans with up to 31 waypoints in each flight plan, so it's pretty safe to say that most pilots will be able to store most all the flight plans that they use for almost instant recall. A press of the Flight Plan button will allow viewing of all the stored flight plans. Highlight the one you want to use, press Menu or the appropriate soft key, and tell the system what you want to do with that flight plan. Navigation on the flight plan page is through the use of the cursor and the FMS knobs. What we're going to do today will be familiar to you if you've watched our GPS approach programs. As we did there, we'll be flying from Sporty's, India 69, to Lebanon, Ohio, India 68. This lets us fly a full GPS approach without radar guidance. Radar would be available if we wanted it from Dayton Approach Control, but that's too easy. We'll do this not as a tutorial on how to fly a GPS approach, but to let you look at G1000 features during an approach. Sporty's has those detailed programs on GPS approaches. Because it's not far, we won't use a flight plan that is stored in the navigator. Instead, we'll do a direct to India 68, then press the Procedures button, highlight and enter Select Approach, choose the RNAV or GPS approach to runway 19, and elect to go in over the Prude intersection. That neatly puts all the waypoints into the active flight plan and readies the navigator to lead us to that runway. On your first takeoff with the G1000, it's helpful to have those airspeed bugs set so that you will have rotation and best climb speeds tagged. We're going to fly this at 3,000 feet, so we'll set that altitude on the G1000's alerter and on the autopilot's altitude pre-select. And before we fly, one thing needs to be made clear. The only interface between the Bendix King KAP-140 autopilot in this airplane and the G1000 is the heading bug and the autopilot's ability to track nav signals generated by the G1000. That lack of other interface means that if the autopilot is to be used, as it should be, we have to set 3,000 feet into its altitude selector alerter. Setting it on the G1000 means exactly nothing to the autopilot. The first time you use the airspeed tape, it might not seem natural because if you fly the same airplane a lot, you might rely on the position of the needle as an indication that it's time to add a little back pressure and go flying. Here it's just a matter of waiting until the number's on the proper value, like so. And now we're flying. The vertical speed is showing a positive rate of climb and the airspeed is increasing. Note that big attitude indication. How did we ever get by with that little round gauge? In fact, after flying this airplane for a while, I had several thoughts when I got back into my senior citizen's airplane. One was that the attitude indicator was awfully small. The other was that a pilot who learned on the G1000 would have a lot more trouble transitioning to an old airplane than would an old airplane pilot have transitioning to a G1000. As we fly along toward Prude, let's look at some of the details on the screens. The inset of the map we put on the PFD comes in handy. On the HSI, we have, as a change is being made, and for 3 seconds thereafter, a digital readout of the heading selected with the bug and of the course selected for navigation. There's always a digital readout of the heading being flown. There's also a readout on what navigational source is being used as the go-to waypoint. We have already gone over the alerts and annunciations that might appear at the bottom of the screen. If there were to be a traffic warning, it would show on the PFD as well as be announced. The target would also turn yellow on the inset and the main map. With this system, traffic is displayed when within 7 nautical miles from 3,000 feet below to 3,500 feet above and includes the location, direction of travel, relative altitude, and climber descent information. The warning comes when, because of altitude, proximity, and closure, the target is deemed a possible threat. The target information is updated with every sweep of the radar, so there's a slight delay, especially when the other airplane's turning. The depiction of its track will lag behind what's really happening. Traffic is also shown over on the MFD. This traffic information is to prompt the pilot to visually acquire the threat. Evasive maneuvers should not be based on this information alone, though adjustments to height within air traffic control requirements are not considered evasive maneuvers. There's a little track pointer ahead of the symbolic airplane on the screen that shows where the airplane will be in 60 seconds at the present heading and speed. I want to show you a neat use of this in conjunction with the traffic information picture. Here we are with traffic showing. In this case, the predictor sticking out in front of our airplane is crossing swords with the TIS indication, which is a clear sign that we either need to visually acquire the target or turn to uncross the swords. In this case, we are VFR, so we just need to turn. We don't need permission from ATC. Any marker beacon indication would also show on this screen. And all the NAVCOM information is shown here along with the transponder status. Up above the PFD in the center is readout of the selected waypoint, the designation of that waypoint, such as initial or final approach fix, the desired track, and the track being made good. These items are fixed. They can't be changed. Why they include desired track instead of bearing to the waypoint, I know not. Desired track is what's set on the HSI. That makes the desired track readout redundant. In fact, with these systems, we can trash the word course and use track to describe everything, because track across the ground is what gets us where we're going. Over on the MFD, the flight plan is displayed on the map. The active leg is colored, and the subsequent legs in the flight plan are shown in white. The wind direction and speed is shown at the upper right. The enunciation of map orientation is there too. The things shown in the top band between the frequency windows can be altered, and for that matter, and as mentioned before, there's a huge selection of things that can be shown or deleted on the MFD. And there's a declutter button that can be used to take things off the map. Press it once to take a little stuff off, press it again to take more stuff off, press it again for an even simpler map, and then press it again to go back to the map that you might have thought was too cluttered to start with. Most pilots will develop a map they like and seldom use this feature. Here we can review the airport to which we're flying. This will tell you all you need to know about runways and frequencies, and you can scroll through the available procedures for the airport. This is accessed through the FMS knobs and using the cursor. There's a terrain proximity page on the MFD where it colors as red terrain that's within 100 feet elevation of the altitude of your aircraft. Yellow is between 100 and 1,000 feet below the aircraft, and black or blank means the airplane is over 1,000 feet above the terrain. As we fly along, the mode in which the GPS is operating is enunciated on the right side of the HSI. It is in the terminal mode now because we are within 30 miles of the destination. The approach has been loaded and activated, and when we're 2 miles from the final approach fix, the mode will switch to active and the CDI scale will go from 1 mile to 0.3 of a mile. As we're flying this approach, the auto zoom feature is active and you can see how it behaves. To me, there's not a lot to like, and this can be deselected and the range adjusted like so. That manual range change was not done on this approach, and I'm showing it to you now just so you can see the difference in auto zoom and doing it yourself. You will notice as we fly along that many of the numbers and enunciations are relatively small. They are big enough, but if your peepers are showing a little age, you will want to select your glasses carefully as you use this system. Approaching Okasi, word on when to turn is given, and if the instructions are heeded, the nav needle will stay in the center. That'll be true even on the 90-degree turn at Noibo. The system has 2 GPS receivers, but they're invisible to the pilot. The system looks at both GPS receivers and uses the one it thinks best. The only way you would know there are 2 would be if one failed. That would show up as a message in the alerts window. By Noibo and inbound. On this close range setting, the precise nature of GPS navigation becomes quite obvious. For the missed approach here, the drill is a climb to 2,000, then a climbing right turn and direct to Mizza to maintain 3,000. Because word is to go direct, not fly a specified radial, the direct button can be pressed to activate the missed approach. Or a soft key labeled SUSP for suspend will set the missed approach up with one button press. In real life, that would be a moot point most all the time because you'd be in radar contact and they'd give you vectors to do whatever comes next. The topographic map looks a lot like grass in a drought in the flat country of Ohio, but in rough terrain it would give a more animated picture. The next thing we'll do is vector ourselves over to the GPS overlay of the NDB approach to runway 22 at Claremont County Airport, home of Sporties. We'll fly this to intercept outside A-Link intersection, or the A-Link waypoint, and fly the approach on in from there. This goes smoothly. One thing that should be noted is that where the direction of a hold is shown on approach charts, it's not shown on any GPS maps that I've looked at. The approach chart is the official word. That is a look at the G1000. There will be old-fashioned fuds out there who will throw up their hands and say that pilots shouldn't depend on things like this. They should navigate with sectional charts, a clock, and a magnetic compass. If they want to say that, okay. Everybody's entitled to an opinion. However, just as an electrical or equipment failure has to be dealt with in a modern airplane, the sectional charts can blow out the window of your J3 Cub and leave you without a clue. This is simply great stuff, and may the good old days never return. Fly this and then get into an old airplane and you'll think you're in a World War I contraption. When I was at AirVenture in Oshkosh in 2003 and glass cockpits in light airplanes were relatively new, I thought that by AirVenture 2004, every new airplane there would have a glass cockpit. That observation was close to correct, and the airplanes that didn't actually have a glass cockpit in 2004 had plans announced for the introduction. Thanks for going along with us as we explored the Skyline with the NAV3 package, which is the term they use to describe the G1000 airplane. Fly safely.